Okay, we're going to do a rigid dynamic analysis in ANSYS Workbench 13. We're going to start with some SolidWorks geometry, a mechanism that we've got. Real simple. It's not really a real-life problem, but it's done so you can best see how the software works. So we're going to put this back, snap this back into position. The big deal here is you typically want to start out with some geometry in a position that you might make sense from a reference standpoint. So we'll flip over to ANSYS, go into Rigid Dynamics, and slide that up to the project schematic. Right click, import geometry, there it is. Check mark, looks good, and then open mechanical. Okay, looks like things came in. Looks good. Okay, so first thing we want to do, let's go and look at connections. So it looks like it created some contacts. We're going to go ahead and get rid of those. Delete that. Then we're going to go back up and look at the geometry. Better yet, let's look at the coordinate system. Here's the global coordinate system. And that did come in at a convenient point. You want to think about that when you're creating the geometry, because things are going to be in reference. The weights and centers of gravities are going to be in reference to this global coordinate system. So you want to bring the geometry in that convenient point. So we'll look at first here the slider slot. I'm not sure why it was a slider slot. It must have been a different piece earlier. But this is the piece that's really fixed. You click on it, and at the bottom here, we'll raise that up a little bit. Graphics properties, visible, yep, transparent, that's okay. We'll change color, maybe make it red. See what that looks like. Can do that. The bounding box, what cube does that fit in? Properties. So it gives you the volume and the mass. Well, let's go back up to the slider slot. Definition here. This is rigid. Here's where you select if you want flexible. You have to do some things different if you want to do that, and we're going to show that later. So for what we're doing, it's really only going to work for rigid right now. Material, structural steel, that's fine. Properties. Here's the volume, the mass, and that's actually the weight. It's a pounds mass. It's not slugs, so it's in English units here. It's actually a weight. Here's the center of gravity, and again, that's in reference to the global. We flip back to the global here. Here's the global. Go back up to the slider slot. What does it say? 50 inches. Okay, 50 inches in the X. In the Y, it's roughly 0. Yeah, those look reasonable. And then the mass moments of inertia. And so it has that for each of the bodies. There's the rod. Here's the rod right here. Here's the pivot arm. Center of gravity, or the inertial coordinate system for the pivot arm, and the cylinder base. Here's the cylinder base. Okay, so let's create some joints. You can do these a number of different ways. From my standpoint, basically what you're doing is you're tying two pieces of geometry together. You're constraining it to move in a certain direction. So we'll grab that one, and we'll grab that one, and that's going to be the revolute joint. And so we'll go back into connections, and this is going to be a body to body. It comes up right here. It's either a body to body or body to ground. So we'll click on body to body, and we want a revolute joint. Okay, so here are the two pieces of geometry you selected. They call it the reference, and there's the red cylinder base, and here's the mobile, and it is the slider slot. So this was actually it was, got that wrong. This red surface is attached to the cylinder base. This blue surface here is attached to the slider slot. And in most cases it really doesn't matter. So we'll go ahead and accept that. Go back up into joints and let's slide this over. Let's create another revolute joint right there. That one, body to body, revolute. Looks good. Another revolute to revolute up there. That surface, revolute. Okay. And now the translational joint for the cylinder. Click out of there. Got that surface, and you'll have to do a control select to get the two surfaces. So there's a translational joint. Take a look at that, and that I'm going to want to change. Notice that I'm going to want to extend the cylinder, and I'm going to want this to be the positive direction. So it has this reference coordinate system. This is the reference coordinate system. So we'll click on that, and in order to move those around, I'll click on this X right here, and I'll click over there and apply, and that'll move the X, and you can do that with any of the axes. The other thing that comes up for each joint is it grays out the degrees of freedom or directions that are fixed, and it highlights the direction that's free to move in. So the cylinder is free to move in the X. This revolute joint is free to rotate about the Z, RZ, that kind of thing. Okay, so we have to have one joint that's fixed to the ground. So basically we'll take this surface right here, and we'll create a body to ground and fixed. Okay, so now let's do the analysis, or prepare the analysis. So we'll right click here, right click, and let's raise this up a little bit so we can see it. We're going to basically translate this cylinder, maybe 10 inches. So we'll go for 50 seconds. We'll use the default time steps here. So we'll leave that as it is. We'll right click, insert a let's do a, we have to turn gravity on. So the standard gravity, it turns out that it always defaults to this negative Z direction, and we want a positive Y, so we'll delete that. So insert acceleration. I want it as components, not a vector. Could be in a vector, but here we want it in the Y in a positive 386.09. Okay, positive being that's the acceleration, and it causes the force in the opposite direction. This isn't on a body, this is on all bodies. So it's going to have the effect of gravity. Okay, so we're going to also insert a, let's slide a translational joint down here. And here it pops in there, and we're going to have an X displacement. Let's go velocity and a magnitude of 0.5, half inch per second for 50 seconds. That should give us 10 inches of displacement. Okay, so for outputs, let's do the cylinder force. So let's grab this translational joint, slide it down into solution, and then let's raise this up a little bit. There's that translational joint. Total force, I only really wanted the total force is good. Let's put it, just give me the X direction, the direction along the length. Y and Z are going to be pretty much zero, so don't need to look at those. And maybe let's look at one of the this joint rotation here. Let's see what that, where is that? There it is right there. So let's slide that down. Let's slide this down into solution. Click on that. And relative rotation. There it is, relative rotation. And that, and it only really gives you the axes that is the critical one. So relative rotation about the Z, and that'll come out in degrees. Looks like we're set. Let's go ahead and solve that. Okay, so if we want to look at the results, we'll go over to this joint probe, which was the force, total force in the x-axis. And looks like initially it was 13,000 pounds was the startup force, and gradually 50 seconds into it, or 5 inches or 10 inches of displacement, it went down to 6471. So we'll animate that. Looks reasonable. Let's look at this displacement. So the displacement, what was this? The slider slot displacement. Oh yeah, here was the relative rotation in the z-axis. So it looks like it went through a rotation of about 20 degrees. You can put a pause on that. You can put it to the position that you want. You can look at the tabular data and get the actual values. If you find one, you can retrieve this result. Retrieve this result, and it'll snap it down to that position. Show you where you're at on the graph. Get a little bit more detail on that. And if you brought the model in and the initial position wasn't where you wanted to start out, there's ways of getting around that. So we'll go back into joints here, and so we're going to configure the, let's say, the translational joint. So it starts out at the initial position, and that again is why you want to think about that before you pull the geometry in. Then there's this configure button. Click on that. This little axis will come up, and then you can move it around. You can extend it and retract it. Oop, put it in the position that you want. And then, let's see, you can do a reset. Let's slide that over a little bit. Revert, puts it back to where you were at. I think you can't see that. It's kind of outside of the screen, but there's a revert button just to the right. So let's pick another joint. Let's pick the this rotational joint here and do a configure. And then we can rotate that. And again, outside of this screen, I'm not sure how I can get that to come up within the screen, but there's a, you can actually key in a certain value and it'll snap to that position. And that can be the position that you may want to start out in. So we'll snap it back to where it was, and that's about it. We're going to do a flexible dynamics problem. We're going to take this same one and basically make that flexible and look at the stresses as it's animating. Thanks for watching.